Hello everyone, welcome to today's presentation. I'm excited to introduce our topic, Applications of Trigonometry. On this first slide, you'll see the title of our session. We'll be exploring how trigonometry is used in various real-world situations. In the upcoming slides, we'll cover different applications, from engineering to navigation. So let's dive in and discover the fascinating ways trigonometry makes a difference. All right, now let's move on to slide 2, which covers the tree height problem. This is where we start applying what we've learned about angles and trigonometry to real-world situations. The tree height problem is a classic example that helps us understand how to determine the height of a tall object, like a tree, using the concepts of angles of elevation and depression. These angles are measured from our line of sight, which is crucial because they allow us to relate the height of the object to a measurable distance on the ground. As we go through this, keep in mind that solving such problems involves understanding the line of sight and how it connects to the angles we observe. This will set the foundation for tackling more complex problems, like finding the height of a kite or other tall structures, which we'll explore later. So remember, the key is how we use these angles and trigonometric ratios to make accurate measurements without needing to climb the object itself. In this topic, we shall make use of trigonometric ratios to find the height of a tree, a tower, a water tank, the width of a river, the distance of a ship from a lighthouse, and so on. Trigonometry is a branch of mathematics that studies triangles and the relationships between their sides and the angles between these sides. It might sound complex at first, but it's really about understanding how the angles and sides of triangles relate to each other. This is incredibly useful in real-world situations where direct measurement is difficult or impossible. So, when we talk about trigonometry, we're essentially exploring the way triangles help us solve practical problems by connecting angles and distances. When we observe children, it's quite common to see them looking up at the sky whenever an airplane passes overhead. And what they're doing is essentially creating a straight line from their eyes up to the plane. This line is what we call the line of sight. It's a key concept because it helps us understand how we visually connect with objects in our environment. When we talk about the line of sight, we're referring to that direct, unobstructed path between our eyes and what we're looking at. Recognizing this is important because it relates to how we perceive and interpret the world around us, especially when it comes to understanding angles, distances, and perspectives in our surroundings. So, in the broader scope of this presentation, understanding the line of sight will help us grasp how humans interact with and observe their environment effectively. Let's take a closer look at the components involved in visual perception. First, we have the line parallel to the ground, which is simply a horizontal line. This line helps us understand the orientation of objects in our environment. Next, we see the line of sight, which is the straight line from the observer's eye directly to the object we're focusing on. This line is crucial because it represents the direction in which we're looking. By understanding these components, the horizontal line and the line of sight, we can better grasp how we perceive and interpret spatial relationships around us. These concepts form the foundation for understanding how vision works in perceiving distance and position. Now, let's talk about the angle of elevation. The angle of elevation is the angle that the line of sight makes with a horizontal line drawn away from the observer's eyes. In simple terms, picture yourself looking up at an airplane in the sky. The angle between your line of sight to the airplane and a horizontal line extending from your eyes is what we call the angle of elevation. This concept is important because it helps us understand how high objects are relative to our position. It's a key idea in navigation, surveying, and even in understanding the motion of objects like airplanes. Essentially, whenever you're looking up at something above your eye level, you're dealing with an angle of elevation. Let's take a closer look at the components of the angle of elevation. First, imagine a line that runs parallel to the ground. That's our baseline. Now, the horizontal line is essentially the flat, level ground itself. The angle of elevation is the angle formed between the line of sight to the object and this horizontal line. So, when you're looking up at an object, like a tall building or a mountain, your line of sight is inclined at this angle of elevation. The key point here is that this angle helps us determine how high or far away an object is, based on the observer's point of view. Understanding these components is crucial because it allows us to analyze and solve real-world problems involving height, distance, and angles. Everything ties back to how we measure and interpret the angles between our line of sight and the horizontal plane. When the pilot of the airplane looks downwards at any object on the ground, the angle formed between his line of sight and the horizontal line drawn away from his eyes is called the angle of depression. This angle is really important because it helps us understand how the pilot perceives objects below the aircraft. Basically, if you imagine a straight horizontal line extending from the pilot's eyes, the angle between this line and the line of sight to the object on the ground is what we refer to as the angle of depression. Recognizing this angle is crucial in navigation and understanding how objects appear from different altitudes. It ties into the overall theme of how angles and lines of sight are used in aviation and surveying to interpret spatial relationships accurately. Let's take a closer look at the components of the angle of depression. First, we have a line parallel to the ground, which helps us establish a reference point for measuring angles. Next, there's the horizontal line, which is crucial because it represents the level of the observer's eye. The line from the observer's eye to the object below is called the line of sight, and this is what we actually look along when observing something below us. Finally, the angle of depression is the angle between the line of sight and the horizontal line. This angle is important because it helps us determine the position of the object relative to the observer. Understanding these components is key when analyzing how we perceive objects at different distances and heights, and they play a central role in our overall discussion of angles and measurement in real-world scenarios. Now, let us solve some problems related to height and distance. 5. Trigonometric ratios. In this part of our discussion, we're going to focus on how trigonometric ratios help us find heights and distances that are otherwise difficult to measure directly. These ratios are fundamental because they connect angles and side lengths in right-angled triangles, which are common in real-world problems involving heights and distances. The key ratios we'll look at are sine, cosine, and tangent. Sine is the ratio of the opposite side to the hypotenuse. Cosine is the ratio of the adjacent side to the hypotenuse. And tangent is the ratio of the opposite side to the adjacent side. Understanding these ratios allows us to set up equations based on the angles we measure, and from there, solve for unknown heights or distances. This approach is powerful because it turns complex measurements into manageable calculations, making it a crucial tool in geometry and trigonometry. So, as we go through some examples, keep in mind how these ratios form the foundation of solving height and distance problems efficiently. Therefore, the height of the pole is 10 meters. Let AB be the pole. In triangle ABC, a circus artist is climbing a 20-meter-long rope, which is tightly stretched and tied from the top of a vertical pole to the ground. Our goal is to find the height of the pole, given that the angle made by the rope with the ground level is 30 degrees. Now, moving on to example 2. Let AB represent the tower, and the angle of elevation from point C on the ground is also 30 degrees. Suppose the point on the ground, where the angle is measured from, is 30 meters away from the foot of the tower. Our task here is to find the height of this tower. Finally, looking at example 1. This slide introduces problem solving with the angle of elevation, which is a key concept in these types of problems. By understanding how to relate angles and distances, we can determine heights and distances that are otherwise hard to measure directly. These examples highlight the importance of trigonometry in real-world situations, especially in scenarios involving heights and distances that are difficult to access physically. Let's consider our scenario with the kite, which we'll call K, and the string tied to a point P on the ground. Now, in triangle KLP, the kite is flying at a height of 60 meters above the ground. The string connecting the kite to the point on the ground is temporarily tied to a point, and we're told that the angle of inclination of the string with the ground is 60 degrees. Our goal here is to find the length of the string, assuming there's no slack. This is a classic problem involving right-angled triangles and trigonometry. The key points to focus on are the height of the kite, which is 60 meters, and the angle of inclination, which is 60 degrees. These give us enough information to apply basic trigonometric ratios, specifically the cosine function, since cosine relates the adjacent side to the hypotenuse in a right triangle. So, in this context, the height of the kite is the side opposite the ground, and the string acts as the hypotenuse. The angle of 60 degrees is between the ground and the string itself. Using the cosine of 60 degrees, which is 0.5, we can set up the equation. Cosine of 60 degrees equals the adjacent side over the hypotenuse. That means 0.5 equals 60 meters divided by the length of the string. To find the length, we just need to rearrange the equation. The length equals 60 meters divided by 0.5, which simplifies to 120 meters. This calculation shows that the length of the string is 120 meters. It's a straightforward application of trigonometry, but it also highlights how understanding the relationships between angles and sides in triangles helps us solve real-world problems like this. Remember, the key is to identify the right triangle and the correct ratio to apply. Let's consider the situation where AC is our original tree. Imagine a storm that causes the tree to break into two parts. Now, after the break, the top part bends and touches the ground, forming an angle of 30 degrees with the ground. The key here is to understand the geometric relationship. The point where the top touches the ground is 8 meters away from the foot of the tree. Our goal is to find the total height of the original tree before it was broken. This problem is a classic example of using trigonometry, specifically right triangle concepts. The broken top forms a triangle with the ground and the remaining part of the tree. The 8-meter distance is the base, and the angle of 30 degrees helps us relate the height of the tree to this distance. Most importantly, pay attention to how the angle relates the height of the bent part to the horizontal distance. Recognizing these relationships allows us to set up the right equations to solve for the original height of the tree. This problem beautifully ties into the overall theme of applying mathematical concepts to real-world situations, like understanding the effects of storms and using geometry to find unknowns. So, as we proceed, keep in mind how these principles can be applied beyond just this example. Now, it's important to remember that height cannot be negative, so the height of the tower must be 6 meters. Next, when we multiply equations, I and Roman 2, we get a new relationship that helps us understand the situation better. In triangle AQS, we analyze the angles of elevation, and similarly in triangle AQR. Since these angles are complementary, if one angle is theta, then the other will be 90 minus theta. Let's consider AQ as the tower's height, and points R and S are located 4 meters and 9 meters from the base of the tower, respectively. The key idea here is that the angles of elevation from these 2 points to the top of the tower are complementary, and they lie on the same straight line with the tower. Our goal is to prove that the height of the tower is 6 meters based on these angles of elevation. This is a classic problem of proving height using angles, and understanding the relationship between the angles and distances is crucial. By analyzing the angles and applying trigonometric principles, we can establish that the height of the tower is indeed 6 meters.